Welcome. We're going to take a quick look at an extension of area between two curves, and we're going to look at two issues that we have with these. Just as a reminder, our general setup is that when we're trying to find the area between some sort of a top function and a bottom function, and we have two different x values that we're looking in between, we can set up this integral, where again, we have top minus the bottom. We subtract those functions and find our integral from our starting point to our ending point. So what we want to look at is the general issue of when this can kind of go wrong, because we noticed in the last video that the setup here isn't too bad if we understand how the fundamental theorem of calculus works. So we've got two problems. The first one is when we're not given endpoints A and B. So here, you'll notice we're just told to find the area bounded between two curves. I've got these things graphed out. You can graph these on your graphing calculator and you'll see a similar picture. The thing to notice is that the area we're looking at is going to be in between these two intersection points. We're looking at this shaded in area here. Now, we're not told that we're looking between an x value of -1 and 2, but we are looking for an area that's bounded in between these two curves, and this is the only region that is. So with that said, we can look at our graphing calculator and use some of the calculation functions on there, or we can just kind of look at it and see that this region starts at an x value of -1 and goes up to an x value of 2. So we'll say from x equals -1 to x equals 2. And again, these are the intersection points of our two curves that we're looking for. So the integral that we set up is going to go from -1 to 2, and we're going to look at our top function, which is the red linear function, x minus 2, and we're going to subtract our bottom function, our blue parabola, that's x squared minus 4, and we can see how things go here. From here on out, we just combine our functions together, use the fundamental theorem of calculus, and see what we get. So I've got -x squared plus x, and then -2 minus -4 is going to be +2. Antiderivatives are not too bad. We're just going to increase our exponent by 1 and divide by that number. And here we've got x squared over 2 and 2x. And we're going to evaluate this from -1 up to 2. Which means what we're going to do is we're going to plug in 2 first. So this is -2 cubed over 3 plus 2 squared over 2 plus 2 times 2. And we're going to subtract what happens when we put in this bottom number. -1 cubed over 3 plus -1 squared over 2 plus 2 times -1. And now we can just start plugging things into our calculator. What we really have here is -8/3 plus 4 over 2 is 2 plus 2 times 2 is 4. And then we have -1 cubed is -1, so this is +1/3 now, plus 1/2 minus 2. And if we plug all this stuff in, we end up with about 3.33 plus 1.67. It's really minus -1.67, but that'll give us 5. You can check my math there just to make sure that I'm okay. But what that means is that the area that we've got shaded here is 5 units squared. And so that's how we can find the area between two curves if we're not given the endpoints. We just have to find those intersection points, look at the x value of those, and then we can set up our integral from there. It doesn't work out too badly that way. The harder problem, I think, is this Bowtie problem. And if you remember, that's where, or if you're seeing this for the first time, that's where our curves are going to cross through each other. And so we're going to switch which function is on the top and which one is on the bottom. So this is what we've got for this example. I've got this nice cubic function here and then a nice linear function as well. And you'll notice they cross right through each other. And I'm looking at this from 0 to 2. So if I don't graph this, this looks like a pretty basic setup, and it can be really easy to kind of mess things up. Let's draw it, graph it out, and we'll see what the problem is. We're going to go from an x value of 0 up to an x value of 2. And if we look at this area, you'll notice that it's really two shapes. The general idea is that if we just did this as one integral, then when they cross over each other, when the curves cross over each other, the area that we'd be looking at would change sign. So if we set this up with the blue function on top, then over in this portion over here, we'd be looking at a negative area. And that's not really what we want. So we're going to set this up into two integrals. We're going to go from 0 up to 1, and then we'll go from 1 up to 2. Again, 1 is our intersection point. We can find that on our graphing calculator using the intersection options on there, or we can kind of eyeball it for most of these. I'll set this up with two different areas that we're finding. So I'll call this A1 for our first area. We're going to go from an x value of 0 up to an x value of 1. And our blue cubic function is on top. So this is x cubed minus 3x squared plus 2x. And then we are going to subtract our red linear function, which is on the bottom. 2x minus 2. Just like before, we can go ahead and simplify this, put our like terms together, and then take a look at antiderivatives, and they'll be pretty easy. Here we have x cubed minus 3x squared. 2x minus 2x is going to go away to 0, and then we have minus 2 dx. So we can take a look at antiderivatives and say this is going to be x to the 4 over 4 minus x cubed minus 2x, and we'll evaluate this from 0 up to 1. I'm going to put a pin in that, and we'll come back to it later. Let's set up our second area, and we'll see how it looks the same, how it looks different, and we'll go from there. Area 2 is going to be this shape here. So this is our first area that we calculated, and this one will be our second one. We're going from 1 up to 2 now, so our limits of integration are going to be different. And you'll also notice that the functions switch which one is on top. So 2x minus 2, our red function, is the one that goes first, and then we're going to subtract our blue function, x cubed minus 3x squared plus 2x. And the nice thing about this is that it's very similar to the integral that we found earlier. We're going from 1 to 2, again this time. And now we're going to have negative x cubed plus 3x squared plus 2. Oh no, I made a mistake. Let me fix this. This is actually going to be minus 2 here. And this one up here is going to be plus. I did the thing that I always warn people about. I forgot to distribute that negative all the way across. This is actually going to be plus 2, and this will be plus 2x. So make sure you get that fixed. Now, our antiderivative is going to be really similar as well. Negative x to the 4 over 4 plus x cubed minus 2x from 1 to 2. And we can kind of put a pin in that. Now, we can find each of these areas, and we will take a look at what those are. And if we just add those areas together, we're going to get the total area for this whole shape. Every now and then, people will get confused. They'll look at these antiderivatives, and they'll say, wait a second, if we add these together, all these terms are going to cancel out, and we're going to get 0. But we have to remember that we still have yet to put in these limits of integration. We're going to be evaluating these antiderivatives at different points. So our total area that we're going to look for is actually going to look like this. It's going to be the integral from 0 to 1 of x cubed minus 3x squared plus 2 dx plus our second area, the integral from 1 to 2 of negative x cubed plus 3x squared minus 2 dx. We already have the antiderivatives, so we'll go ahead and take a look at those in a second. We'll find our areas, and we'll see what goes on from there. But this is our total area that we're looking for. All right, I'm going to skip back to the next page. I'll probably have to skip back and forth while I copy some things down. So let's find area 1. We said that was x to the 4 over 4 Then we had minus x cubed plus 2x. And that was from 0 to 1, I believe, right? Yeah. Okay. I can never remember stuff like that. Anyways, we'll go ahead and start evaluating this. Plug in our first number, 1 to the 4 over 4 minus 1 cubed plus 2 times 1. And we'll subtract what happens when we put in our second number, 0 minus 0 plus 0. That's pretty boring. So we end up with a quarter minus 1 plus 2. That's 1/4, sorry, minus 4 over 4 is negative 3 over 4, plus 8 over 4 is positive 5 over 4. So that's our first area. Our second area, we said, was negative x to the 4 over 4 plus x cubed minus 2x, and we're going from 1 up to 2 now on this thing. So this one might be a little bit more annoying to do. We're going to plug in 2 first, figure out what that is, and then we'll subtract what happens when we plug in 1, which we already know what that is. Kind of. The signs are going to be a little switched. So we've got negative 1 over 4 plus 1 cubed minus 2 times 1. All right, so this is negative 16 over 4 plus 8 minus 2 minus negative 1/4 plus 1 minus 2. So this is really negative 4, plus 8 is positive 4, minus 2 is 2. And now we've got negative 1 over 4 plus 4 over 4 is 3/4, minus 8 over 4 is negative 5 over 4. You'll notice it's just the opposite sign of this because all the signs are switched. So we're going to say negative 5 over 4. So we're really adding these things together. So we have 8/4 plus 5/4, which gives us 13/4 total. Now, again, this is just the size of area 2. Our total area, if you remember, was these two things added together. So we've got 18 over 4, which is 9 over 2, or if we prefer, 4.5. So that's the size of this area that we have shaded in. This first area here was 5/4 units big, and this second area here was 13/4 units big. We can add those two things up and see how all that stuff goes. Those are our two problems that we've got. If you've got any more questions on those, feel free to let me know. But other than that, we've got everything we need to find the area between two curves.